just wanted to make a quick video going over how to do this practice quiz number 2. So if you have to figure out the type of bond, you are going to your periodic table, and I don't have one on me, but I'm just going to show this one that's online. You're going to your periodic table, you're finding that bold staircase that goes along your periodic table, and remember, metals are on the left-hand side and on the bottom, non-metals are on the right-hand side. Don't forget that even though hydrogen's on the left, it's a non-metal. And you're going to figure out what types of atoms you have on either side of the bond, and that's going to tell you if it's covalent or ionic, and then you can further figure out if a covalent bond is polar or nonpolar. So if you have metal-nonmetal, it's going to be ionic. If you have only nonmetals, it's going to be covalent. So in this first one, CC, only nonmetals, I know it's going to be a type of covalent, so electrons are shared. That's the definition of covalent. Make sure you know that definition. If I then see two of the same nonmetal that have the same electronegativities, so they have the same attraction for electrons, so those electrons would be directly shared exactly equally between each of those, so it would be a nonpolar covalent bond. So if you see two of the same nonmetals, nonpolar. If you see two different nonmetals, these are each nonmetals. Okay, if I go to my periodic table, here's C, here's N, they're both to the right of that bold staircase. So these are two different nonmetals with two different electronegativities, so this is a polar covalent bond. The electrons are going to be closer to the more electronegative atom, in this case N, so essentially they're not shared equally. So you really just need to know those definitions of polar is an unequal sharing, nonpolar is an equal sharing. If I don't give you electronegativity values, you're just saying, okay, two different nonmetals, polar, two same nonmetals, nonpolar. I will never give you two different nonmetals that have the same electronegativity unless I gave you the electronegativity values and asked, hey, which of these is nonpolar, and you don't see an option where there's two of the same, then you would look up the electronegativities and just look for a difference of 0. So nonpolar always have the same electronegativity, so the difference is 0. So you're looking at typically two of the same atom. Okay, here's two nonmetals that are the same, nonpolar. Here's metal nonmetal, ionic. Here's metal nonmetal, ionic. Okay, here's two nonmetals. So it's covalent, but they are the same atom, so it would be nonpolar because they have the same electronegativities. The difference would have to be 0 if you have two of the same element. And here's two different nonmetals. That's polar covalent. Here's a metal and a nonmetal. It's ionic. Okay, you can then tell if a bond, if given a couple of different polar bonds, you can tell which would be the most polar by seeing which would have the biggest difference in electronegativity. If I give you values, here I did, then you would just subtract. So F and Cl, I would subtract, I'd find the difference between them, and then I would do the same thing for H and F, subtract, find the difference between them, and see which is the biggest difference. Always do the bigger number minus the smaller number, so you're comparing a positive value. So for FCl, F has a 4 electronegativity, Cl has a 3, so that's a difference of 1. H and F, 4 and 2.1, that's a difference of 1.9, so HF is going to have the biggest difference in electronegativity, so that is the more polar bond. And typically if we have ionic compounds, metal, nonmetal, we don't say it's a polar bond because it's not covalent at all, so we wouldn't want to pick something that's ionic for this. If we asked what's the most ionic, we say which has the greatest ionic character, and you might have seen that in the video on that particular section. Okay, so that's one part of the things we learned. The other thing we learned about is how to use this chart. So essentially, if I give you a structure of any sort, the first thing you want to do is figure out how many electron domains there are, and then you can figure out what's called the overall electron geometry. I'm not usually going to ask too much about that. I'm more going to ask about the molecular geometry. So to get the molecular geometry, we need one more piece of information, and that's figuring out the number of lone pairs. And then based on that, so let's say I had 3 domains, no lone pairs, then I can figure out what the molecular geometry is. I could see what the structure would actually kind of look like in a 3D format. I would see the bond angle, so between all these y's they'd be spaced 120 degrees, which makes sense, it takes up a circle, and I can see that, which we'll learn in the next lesson, that these structures are typically going to be nonpolar as long as all the atoms on the outside are the same, so all these are Y and not something different. So like I was saying, you want to first look at your central atom, and you only do this on a central atom. You don't do it on outside atoms, and you count the number of domains. To get the number of domains, you're kind of looking at how many places are there electrons of any sort, whether it's in the form of a bond of any type, single, double, triple, or whether it's the form of a lone pair, 2 dots. So on this carbon, here's 1 domain, that's a bond, 2 domains, 3 domains, 4 domains. 1, 2, 3, 4. It's like how many sides are on that carbon. 4 domains, and none of them are lone pairs. So if I go to the chart, 4 domains, none of them are lone pairs. Okay, number of lone pairs, that's tetrahedral. All the angles between them would be 109.5. It would look kind of like this in a 3D structure. These are typically going to be nonpolar molecules, though they can contain polar bonds. The entire thing might be a nonpolar molecule, and we'll talk about why next lesson. Okay, so doing the same thing for this one, this has 1, 2, 3, 4 domains. Electrons by themselves or bonds count as a domain. So 1, 2, 3, 4. Okay, 1 lone pair, if I use my chart, it's trigonal pyramidal. This has 1, 2, 3 domains. One of them is a lone pair. 3 domains, one's a lone pair. That's bent. So I'm really just using my chart. Just remember that a bond of any sort counts as a domain. 1, 2, 3. And lone pairs, 2 dots, count as 1 domain. Okay, this has 1, 2, 3 domains, no lone pairs, so it's trigonal planar. This one has 1, 2, 3, 4 domains. One of them is a lone pair, so this is trigonal pyramidal. This has 1, 2, 3 domains. One of them is a lone pair, so this would be bent. And notice that the structures I gave you, sometimes they kind of look like the 3D structure given on your chart, like BCl3 is trigonal planar, that kind of looks like this. Other times they're given just without showing the geometry, so this really should be bent. 1, 2, 3 domains, 1 lone pair. It should really look like this in 3D life, but since it's just a practice structure, they didn't draw it that way. So don't say, oh, this looks like it's 180-degree angles, this is linear. Don't just use the structure to do that. Count the domains, figure out how many lone pairs, that will be the geometry. So in reality, this is actually kind of a bent structure. Same with this one, should be a bent structure. Okay, if you have more than one central atom, you just do the same thing but on each central atom. So I don't want to do this H. This oxygen has 1, 2, 3, 4 domains. 2 of them are lone pairs, so it is bent. Even though it kind of looks straight or linear in this picture, it actually should be bent. This carbon, doing the same thing, has 1, 2, 3, 4 domains. Tetrahedral. This carbon has 1, 2 domains. Remember, a bond of any sort counts as 1 domain. 1, 2 domains, so it's linear. This one is also linear. 1, 2 domains. This carbon has 1, 2, 3 domains. Trigonal planar. This one has 1, 2, 3 domains. Trigonal planar, and I don't do it on the outside ones. Okay, you can also figure out if there's any polar or nonpolar bonds in the whole structure. So remember, a bond is just between 2 atoms. So here, H and O, this is a bond. Okay, this is a polar covalent bond because it's between 2 different nonmetals. They would have 2 different electronegativities, the difference would be greater than 0. But if you have 2 different nonmetals, we could safely pretty much assume that it's going to be polar of some sort, and 2 of the same would be nonpolar, though there are some exceptions of elements of the same electronegativities, but I didn't give you any values here. Okay, O and C, that would be a polar bond. Okay, C and C, these are all nonpolar bonds here because they are all between 2 elements that are the same and have the same electronegativity. CCl, that's a polar bond. And CH, those are 2 different nonmetals. We can say that's a polar bond. It actually has a difference of about 0.4 or so. So some textbooks say, oh, this difference is so small it could be negligible, and we could say it's nonpolar, but I would accept that as being polar. I would accept it as either way. So hopefully that helps to explain a little bit of this to help you understand these concepts.